Can better action representations unlock more generalizable and efficient robotic manipulation? In this paper, we introduce HiST-AT, a hierarchical spatiotemporal vector quantization framework that learns structured spatiotemporal robot actions. Hierarchical spatiotemporal action tokenization means transforming continuous robot manipulation trajectories into structured multi-level action tokens. Here we see an example of robotic manipulation, where a robot performs a complex task sequence, and our model organizes these actions into fine-grained sub-actions and higher-level action structures over time. By jointly modeling spatial precision and temporal smoothness, our model enables robots to better understand, transfer, and generalize manipulation skills to unseen tasks without retraining. Despite the promise of in-context imitation learning, learning effective robot action representations remains highly challenging. Current approaches often lack temporal smoothness, producing abrupt or unstable action transitions that reduce execution reliability during long-horizon manipulation tasks. Many existing methods also suffer from weak generalization, limiting their ability to transfer learned behaviors effectively to unseen tasks or environments. Additionally, flat tokenization strategies fail to capture the hierarchical nature of robotic actions, making it difficult to represent both fine-grained motor primitives and broader task structures. These limitations are further compounded by inaccurate action boundaries, where poor segmentation can misrepresent critical transitions between manipulation phases, ultimately reducing policy precision and adaptability. In-context imitation learning enables robots to generalize from demonstrations to new tasks without retraining, making the action tokenizer essential for capturing demonstration data effectively. Previous action tokenizer methods rely on vector quantization with flat clustering, focusing exclusively on spatial cues by only recovering the input actions. To overcome these limitations, we propose a hierarchical spatiotemporal action tokenizer, HiST-AT, that utilizes multi-level clustering to capture complex multi-layered action structures. Furthermore, our approach explicitly exploits both spatial and temporal cues by jointly reconstructing the input actions alongside their corresponding timestamps. By successfully extracting these hierarchical structures and spatiotemporal dependencies, our method solves these challenges. Our novel method, HiST-AT, first feeds a sequence of robot actions X into an encoder F theta. The encoder maps these actions into a latent representation V, which is then refined through a Lipschitz-conditioned regularization layer, F psi, to ensure temporal smoothness. These regularized embeddings, V, undergo a first level of vector quantization using codebook Z, which assigns each vector to the closest subaction prototype to capture fine-grained motion primitives. After further regularization through F omega, these representations are mapped to a second codebook A, grouping subactions into high-level action prototypes and establishing a clear hierarchical structure. To stabilize the hierarchical clustering, we apply commitment and codebook losses at both quantization levels, ensuring the latent vectors stay closely aligned with their respective subaction and action prototypes. The spatial reconstruction loss is then calculated by passing the high-level action tokens, QA, through a spatial decoder to recover the original robot actions. Simultaneously, the temporal reconstruction loss is generated by feeding the intermediate subaction tokens, QZ, into a temporal decoder to predict the associated timestamps, enforcing timing awareness. These dual reconstruction losses work together to capture both the physical execution and the temporal progression of the task. Combined with hierarchical and Lipschitz regularization, these spatiotemporal objectives guide HiST-AT to learn robust, transferable action representations for complex manipulation tasks. Our approach establishes a new state-of-the-art by consistently outperforming previous methods in terms of success rate across all tested environments. These results validate that leveraging hierarchical clustering and spatiotemporal cues leads to more effective and generalizable action representations for in-context imitation learning. To analyze the individual impact of each module, we conduct an ablation study of model components on Robotics. Our complete HiST-AT model achieves the highest success rate when all components are integrated. Utilizing hierarchical clustering alone leads to a significant performance boost over the baseline, underscoring the necessity of capturing structured action primitives. While spatiotemporal reconstruction independently provides a noticeable improvement, it is less substantial than the gains from hierarchical modeling. Finally, combining both modules results in a 6% average performance increase compared to the baseline. Here we show qualitative results of HiST-AT performing a door-closing task on the Robotics and stacking cube on the MANI-scale benchmarks. Our method produces trajectories that target interaction zones with high precision, ensuring reliable alignment with the door handle throughout the motion. The hierarchical tokens enable fluid transitions between task phases, maintaining temporal smoothness even during complex manipulation. By integrating hierarchical vector quantization with joint spatiotemporal reconstruction, HiST-AT extracts complex action structures directly from expert demonstrations. Our framework produces smoother trajectories, more distinct action primitives, and superior generalization across diverse robotic benchmarks than prior work. We believe this establishes a new state-of-the-art for scalable and effective in-context imitation learning. If you're curious, check out the full paper on arXiv, or feel free to reach out. We'd love to hear your thoughts.